Sorry, one moment.
That's okay.
All right. Sorry about that.
Okay. So how's your summer been?
It's been pretty good, thanks. How's yours been?
Good. Good. And you are starting your junior year at Chatfield?
Sophomore year at Mullen.
Okay. You know what? I thought I remembered Mullen. And when I saw their instructions on this packet, this PDF file you sent me, I said to myself, that sounds like Mullen. They're the only ones that make you do math in the summer before you even go back. So when's your first day of school back?
Tomorrow, actually.
Oh, really? Wow.
Yeah.
So you have this test tomorrow.
I don't think it's a test, but we just have to turn it in.
Okay. All right. I guess we can just start at 1, and we'll only do problems where it looks like you have difficulty with.
Oh, I went through the packet already.
Okay.
And I have like 7 problems that I need help with, if that's okay.
Perfect. You tell me which ones they are.
Okay. So, just trying to find everything. First one was 11. You had to factor and solve that one.
Okay. What's the first factoring step to take on 11? In other words,
I don't think we have.
Whenever you're factoring something, you should always kind of do it in a certain order. The very first thing you want to look for is there a greatest common factor? If there is, factor it out. In this one, there is. What's the greatest common factor?
3?
No. Remember that the greatest common factor has to divide into every term evenly.
Oh, x squared.
Correct. What's left over?
X squared plus 6x plus 9.
Now we have a quadratic that's pretty easy to factor. Don't forget to bring the x squared down. How does this quadratic factor?
It's just plus 3, x plus 3, x plus 3.
So what are my answers?
-3.
And?
0.
Yeah, everybody forgets that one. Remember, what we have is 3 things being multiplied together. So any of those 3 things can be equal to 0. One of them has to be equal to 0. We know that. But that can be equal to 0, that can be equal to 0, or that can be equal to 0. Okay? So always look for the greatest common factor first. In fact, I like to list them when I'm teaching people algebra. That's the first one I look for. Second one I look for is this. What's DOPE stand for?
No idea.
Difference of perfect squares. In other words, how does this factor?
Wouldn't it be x plus 5 and x minus 5?
Yeah. Okay, and notice the difference. There's no greatest common factor there. It's also not a quadratic that I can factor unless I know a difference of perfect squares. Now, I'm guessing you had problems with 13 also.
Yeah, and 12 also.
All right, let's do them in order. All right. They've taught you how to factor cubics, correct? But using one technique only. In other words, cubics are actually horribly hard to factor. They are. I mean, people think quadratics are hard when you have to use the quadratic formula, but nothing's harder than cubics and quartics to factor. Extremely complicated, extremely time-consuming, except in one case, and that's where you can group them. Now, what do you need to be able to group it? You need this coefficient over this coefficient to be the same ratio as that coefficient divided by that coefficient. Well, they are. They're in a 1-to-2 ratio, right? Okay, watch what happens when I group it. First thing I'm going to do to group it is separate them into two expressions and put parentheses around. So I do this first. What goes here?
16x minus 32.
Notice, every step of the way, check your work to see if it's the same function. Our goal here is to not to change it. Did we change it?
Nope.
Yeah, we did. That's not a minus 32. It needs to be plus 32. See why?
Yep.
In other words, this negative sign has to get distributed to both of these terms. So when you group it and you add this second set of parentheses, always make sure you check the sign on that number. Most people will make the same mistake you made. Okay? So very important. Now we got two different things in parentheses, and we can take a greatest common factor out of each. What's the greatest common factor out of the expression on the left?
X squared.
Leaving?
Plus, so it'd be x plus 2.
The greatest common factor of the expression on the right?
16.
Leaving?
X plus 2.
That's the key. Both expressions in the parentheses have to be the same, otherwise this technique's not going to work. And it only works is if these ratios are the same ratio. But notice that if I'd have made that mistake and left it minus 32, not spotted it, then this would be x minus 2. Well, I can't do anything with an x minus 2 and an x plus 2. But I can do something with that. What can I factor out of that? Is there a greatest common factor? Yeah. It's just unusual because you're not used to factoring out binomial terms. Most of the time when you're factoring out a greatest common factor, you're factoring out a monomial, a single term. What's left over?
X squared minus 16.
Yeah. Now, all of that's equal to 0, but we can factor the x squared minus 16 into what?
4. X plus 2, I mean x plus, yeah, sorry.
X minus 4 times x plus 4. In other words, a squared minus b squared always factors into a minus b times a plus b. Once you get the first one, the second one's automatic. Okay? And now what three solutions do I have?
4, negative 4, and negative 2.
Yeah. And that only worked because I could group it. If I change this number to a 30, it turns into a 20-minute problem. Maybe a 30-minute problem. And its solution is one that I don't think you've even learned yet, which is the rational factor theorem, which says if you have a cubic and there's a factor, the numerator has to be a factor of the constant and the denominator has to be a factor of the coefficient of the x cubed term. But like I said, that is an extremely complicated and difficult technique. And that's why they start off teaching everybody the ones that can be done by grouping, like this.
Okay.
So when you see a cubic, that there's no greatest common factor. Notice that I cannot take anything out of all four terms. Next thing to check for is, can it be grouped? And at this point, it's always going to be able to be grouped because they haven't taught you the other method. In other words, until they teach you that more complicated 30-minute method, the only way you're going to be able to do any of these cubics are by grouping, if you can do it. Now, 13, what is that called?
Different of perfect cubes.
It's sum of perfect cubes. Okay, let's go over these. Here's difference of perfect squares. Now, I think that it should always be taught a minus b times a plus b. I'll explain in a moment. Obviously, a plus b times a minus b is the same thing, but this is all about memorizing stuff. Okay, and how best to memorize it? Well, there is no sum of perfect squares. A squared plus b squared does not factor. But there is a difference of perfect cubes, and the first term is always a linear term with the same sign. Notice, top and bottom. First term is always linear with the same sign as we're dealing with. Second term is a squared. This is always the opposite sign, a plus, ab plus b squared. So that's how difference of perfect cubes factors. And sum of perfect cubes also factors. Turns out that as long as it's an odd number, both sum and difference factor. If it's an even number, you only have the difference of perfect. Okay? Now, here the first term is linear, same sign, plus. Second term is exactly like this one, only opposite sign for the middle term. Now, if you can notice the pattern there, it makes it a lot easier to memorize these. But the biggest pattern is this very first term is linear and has the same sign as what you started with. And the second term always has the other sign as the middle term. Okay? So we're looking at the sum of perfect cubes here. So tell me how this is going to factor.
So it'd be x plus 3 x squared. It's like minus 3x plus 9.
Good. And just for your information, this never factors again. That's never a quadratic that can be factored normally. So you don't need to spend any time trying to see whether that factors. Okay. And okay, that's enough on that. But you definitely want to memorize these three right here.
Okay, thank you.
Sure. 14?
Yes.
This looks like a quartic, which would make it really tough. But it's what I call a quadratic in disguise. In other words, what something needs to be a quadratic really is only one thing, and that is that this term be this term squared. Okay? There's a number of ways to look at this. Let's look at a way called U substitution. If I let U equal x squared, the middle term, well then what's U squared? U squared is x to the fourth, right? Now I can rewrite this. it now becomes u squared minus u minus 12 equals 0. Well, that's a quadratic that I can factor really easily into u minus 4 times u plus 3. And now I go back and I resubstitute. Well, that's the same. U is x squared minus 4 times x squared plus 3. And then I can go further in that that's the difference of perfect squares. So how's that factor?
X minus 2 plus 2.
That's good. What can I do with this x squared plus 3? Can that ever be equal to 0?
No.
No. So there's really only two real solutions to this. And that's x equal 2, x equal minus 2. Now, I can try to solve it. I'll set x squared plus 3 equals 0, which makes x squared equal minus 3, which makes x what? Plus or minus, first of all. In other words, whenever you solve an equation by taking the square root of both sides, always start your answer with plus or minus. Most people leave it off, and you'll always lose points for it. Okay? So just kind of get in a habit of, if you're solving an equation taking the square root of both sides, which you did, start your answer off with plus or minus. And it turns out you're right. It's the square root of 3i. Okay? So this is a quartic, and we would expect 4 solutions. We expected 3 solutions from the cubic. We expect 4 solutions from the quartic. Well, we got them. There's 1, there's 2, there's 3, 4. So let me just give you another example of a quadratic in disguise. Notice why this is a quadratic. It's because if I square e to the x, I get e to the 2x. So again, you could use substitution. You don't necessarily need to use substitution. In other words, I know that this has got to be e plus 4 times e minus 3, and it produces this quadratic. Excuse me. E to the x plus 4 times e to the x minus 3. Apologies. That produces that quadratic. And then you have to solve each of these separately. But I won't spend a lot of time on that because I know you just want to get to your 7 problems. What else?
Okay.
Yes, 16.
16. Let me see. Hold on. Yeah, 16 was one of them.
Because we're trying to solve for, well, what's the first step? An obvious first step.
Subtract 11.
How about we subtract, this is a slightly different problem. This is not a quadratic. There's no x squared term. Okay.
So subtract 7?
Yeah. In other words, when you have linear equations, you try to get all your variables on one side, all your numbers on the other. Totally different with quadratic equations. Quadratic equations are where you try to get everything on one side and 0 on the other. But if I subtract 7 here, then I have 2ax plus bx equals 4. Now I'm trying to solve for x. What's the next step?
Divide by 2a.
Divide by x. Factor out an x. What's the greatest? Look at that in terms of, is there a greatest common factor? Factoring is so frequently the solution to math problems that it should always be in the forefront of your mind when you're trying to solve something, is can I factor this? Can I factor?
No.
I can factor.
Well, you can factor out x.
Okay, what's left over?
2a and plus b.
And now check to make sure we haven't changed it. We haven't. So what's x equal to?
4 over 2a plus b.
Yeah. In other words, that coefficient doesn't have to be in front to be able to get rid of it. Still just a coefficient. So the answer to a lot of problems that look like this is that factoring. Factor a greatest common factor out. Okay. What else?
I was a little confused on the 21 and 22.
Okay. You're good with these inequalities that
yeah, I got them.
Where you have to change the direction of that sign if you divide by a positive or a negative number?
Yep.
Okay, good. All right, let's talk about what this means. If I say something like that, means two things, always. Separated by an or in the middle. I'm going to write the first thing over here, and the first thing is the same thing I just wrote without the absolute value sign. But the or part is same thing always in the middle, never change what's inside the absolute value, but now you have to turn the sign around and put an opposite sign on the number like that.
Okay.
Now solve each one vertically. The reason I write them horizontally with an or in between is because I know I'm going to have to solve them vertically. Well, x is greater than minus 1, or x is less than minus 11. And you'll see that that works. As long as x is greater than minus 1, this is a true statement. But hold on a second. Excuse me. That's a 10. I probably confused the heck out of you. There's my two answers. I went to write 10 and it came out 0. In other words, the first thing you write is that exact thing without the absolute value. That's what this is right there. It is the exact thing without the absolute value. And the second thing you write is the same inside part, opposite sign, opposite sign. So you have to do two things for the second part. And then when you solve them, you get these answers.
What about when it's equal to each other rather than greater than or less than?
That's actually quite a bit easier because there's really only one thing you have to do. If there's an equal sign there, then that means x plus 1 is equal to 10, or x plus 1 is equal to minus 10.
Okay.
Just remember, never change the inside part. Don't mess with that. Everybody wants to mess with that. The only parts you need to mess with are there, and if there's an inequality, it needs to be reversed on the second part.
Okay.
Okay. So for this problem, what's the first step?
I divided by 3.
Yeah, we always want to try to isolate. We want to get it down to something that looks like this. Now, what are the two things I can write?
X equals...
Hold on, let's do it step by step just so I know. X minus 4 equals?
3.
1/3. In other words, the very first thing you want to write is exactly what that says, only without the absolute value sign. You see how that's exactly the same, only take away the absolute value sign?
Uh-huh.
That's always what you want to do. The first part is easy as pie. Second part is what?
X minus 4 equals negative 1/3.
Yeah, now you have two very linear, very easy equations to solve. Okay, let's save time. Let's save time by doing 22. Similar thing. In other words, if you can get rid of anything that's with your absolute values but outside of it, do that first.
So divide by 4.
Yep. So now we have this, and it's a positive 4, not a negative 4. If it was a negative 4, I would have to switch it immediately. In other words, whenever you have an inequality and you're dividing or multiplying by a negative number, you have to switch the direction of the thing. So now what two things can I write? X
minus 1 is greater than 3, or x minus 1 is less than negative 3.
Yeah, there you go. And then, again, it's pretty straightforward. What's this solution?
4.
X is greater than 4.
X is greater than 4. X is less than 2.
Negative 2.
Negative 2.
I'm adding 1 to that negative 3. Okay. Now, I'm just going to add one last thing about graphing these. You always graph them on a line, not a XY grid, because we don't have a Y's, all we have is X's. Well, here's 4. Here's minus 2. First part says X is greater than 4, so it goes like that. Second part says X is less than minus 2, so it goes like that. But that's the way you graph these.
Okay.
What else?
How much time do I have left?
Well, I can go another half hour if you want. Or I can go 15 minutes. I mean, we can go whatever, and I'll proportionally charge you for it. You won't...
Can I go 15 minutes more?
Sure, sure. And I'll just charge you for 3/4 of an hour.
Okay. Here, 1 second. Let me go get some paper.
Okay.
It's the very last page. It's called Car Loan Project.
Okay. You're good with all of these composite functions?
Yeah. Could we check the answers to that?
Well, tell me what f of minus 3 is on number 23.
I said that was 27.
Okay, good. Yeah. The secret to parentheses notation like f of x and g of x is whatever's inside the parentheses, you plug it in for x. As simple as that. No matter how complicated. Okay? So let's look at 26 just for a moment. It says g of minus 3. Well, I'm going to do this one step at a time. First of all, what is the inside? What is g of minus 3 equal to?
I said that was negative 2 times negative 3 plus 5.
Which is?
11.
Okay, so that's the same as g of 11. Now what's g of 11?
G of 11 is negative 2 times 11.
Okay, so negative 22 plus 5. Don't forget the plus
17.
Right, negative 17. So that's the answer for that one. And
okay.
Over here, you're going to do a similar way. Do the g of 1 first. It's going to give you a number. Then stick the number and do f of whatever that number is. So composite functions are pretty easy. once you get the method and the pattern down. Just always start from the inside and work out.
Okay.
The car loan project, is this what we're looking at?
Yeah, actually, I think I'm fine with that, to be honest.
Okay.
I thought it was going to be tough, but the more I look at it, I think I'll probably be fine.
Let's talk about one thing with car loans. What we're talking about is exponential expressions here. If you deposit $100 in a bank account earning 5%, what would it be worth after 5 years or 6 years, say? Well, you'd get that by, there's your $100, your starting amount. 5% we need to convert to a decimal. And I said 6 years, that's what T is in years. So the total amount would be 100 times the number 1.05 to the 6th power. Well, 1.05 to the 6th power is probably like 1.4 or 1.6. And so your money would grow to approximately $160 or $150. But all of these kind of problems are going to be dependent on one of three equations. This is simple interest, meaning calculated once a year. There's another one for if it's calculated more often per year. And there's a third one if it's calculated continuously. I don't see any continuous ones on here. It looks like you have interest rates that are all okay, but anyway, that covers compounding stuff. It also covers decay. If you have a certain amount of radioactive material that is decaying at 20% per year, then this R becomes a minus 0.2. And you can figure out how much you have left at the end of a certain...
So if it's under 1, then it should go, it'll decay, but if it's over 1, then it'll rise.
Exactly.
I was wondering if you could label everything, if that's okay.
Sure. This is ending amount. And I'm not sure this exactly goes to the car loan question. I haven't had time to read this question. This goes more towards if you put money and it grows, or if you have something and it's decaying. That's the ending. This is the initial. Let me label it the initial amount. This is the interest rate. And that is T, and that can be in anything, it depends. Usually it's time in years. But it can be time in days. Depends on the problem. In other words, you have certain radioactive material that will decay. It has a half-life of 2 days. So they make T in days instead of years. Now, this is only if it's compounded yearly. Let me give you the other two equations, just so you're going to need them at some point. The other one is this one, but now it's 1 plus R divided by some K times K times T. And K is the number of times per year that it's compounded. In other words, if you get a bank that'll compound it monthly, K is 12. If you get a bank that'll compound it daily, K is 365. And there's lots of different deals out there, so this one isn't found in nature so much, well, nor is this one for that matter. Both of these first two are not natural. They're creations of man having to do with car loans and bank accounts and appreciation. And the third one, this is the one you find in nature. A is equal to E to the RT. Oh, starting amount, A1. So it's AE to the RT, E being the number E.
Mm-hmm.
And this is for continuous compounding. By that I mean every second your bank account is earning that interest rate based on what it's at that particular second.
Mm-hmm.
Or another way to look at it, I could say K is approaching infinity. Right? Because if you're compounding continuously, you're compounding an infinite number of times per year.
Mm-hmm.
So these three equations are the ones you're going to need, and it depends on the situation as to which one you use. This is for once a year compounding, this is for more than once a year compounding, and this is for continuous compounding.
Okay.
Now, for loans, calculating the monthly payment, it's a little different. That's actually a rather specific equation that I don't have memorized off the top of my head. Do you have your calc book yet, or your pre-calc book?
No, not yet, unfortunately.
You have your book from last year,
Yeah.
which was an Algebra 2 book?
Yeah, I don't think I have it anymore, though.
Well, I'm not sure that this equation or formula that you need is even in it. So it kind of sticks you. It gives you, let's see. It wants you to go to these links. I'm trying to read it real quickly. Yeah, this is not a math problem as much as you have to go, see this link right here? You can get an amortization calculator, which will give you what your loan payments are in each of these 5 conditions. In other words, let's say you take one loan out at 5% for 5 years. Well, I can't use one of these 3 formulas over here on the right to calculate what that payment is. I'd have to use a calculator.
Uh-huh.
Okay, you're going to have to go to this link, use their calculator. It's called an amortization calculator, and it tells you what your monthly payment's going to be.
Okay.
Now you can answer number 3. Well, the lowest interest rate is clearly number 1. But the smallest monthly payment might not be number 1, might be number 2. The calculator will tell you that.
Okay.
The shortest time is clearly number 4, it's 2.5 years, and the loan with the lowest cost. Well, the cost is your monthly payment times how many months you have to pay. You multiply those 2 things together, and that gives you your total cost.
Okay.
Okay, so that's the way to do this. Step 1 is to go to that link and figure out what the monthly payment is on each of these 5 loans. And once you do that, the rest is kind of easy.
Yeah, seems pretty easy.
But you do need that amortization calculator. I'm really surprised they give you a problem like this.
Yeah.
Yeah, it's just, especially since they haven't given you the formula for coming up with that monthly payment. There is a complicated formula for it. Like I said, I don't have it memorized, but You don't need to memorize it. They're not asking you to memorize it. All they're asking you to do is use this calculator to come up with what your loan payment would be under these conditions.
Okay.
Okay? All right, Jacob. Well, listen, it was good to hear from you again.
Yeah, it was good to hear from you too.
Yeah, I hope to work with you this year. Mullen's a good school.
It is. It's really hard.
I am impressed with their math program as any school that I've ever worked with.
Oh, really?
Yep. I had one student once, and they forced him over the summer to make flashcards of like 50 different flashcards and then use them to memorize all that stuff.
Wow.
But the key was they wanted him to turn in the 50 flashcards when he was done. In other words, they wanted to make sure you do those flashcards yourself. And you don't go online and, use some digital flashcards that you get off the internet. Because part of memorizing it is accomplished when you make the flashcard. And Mullen's the only school I've ever known that did that. And I do it now when I have students that are trying to memorize stuff that's a lot of stuff to memorize. I suggest to them they make up flashcards and they practice them. Best way to do it.
Yeah, it is.
I can't click on this link, but you probably can in your computer, because I opened this with a special, not a PDF, it's a PDF reader, but it doesn't let me click on these links. But when you click on that link, it'll take you to an online calculator that will let you put in that interest rate and the length in years of the loan.
Okay.
You might have to make up a number, because I noticed they didn't give you any kind of amount. So
yeah, I think you have to find it probably.
No, there is no amount. It depends on the car you're buying. You might buy a $10,000 car, you might buy a $20,000 car. I'm just saying that the calculator is going to require an amount. You're not going to just be able to put in 5% for 5 years. It won't tell you anything. You're going to have to say, I'm going to borrow $10,000 at 5% for 5 years. And then use the same $10,000 for each of the 5 loans.
Okay.
Then you can compare your total cost on each one.
Okay.
In other words, that's a real life problem. You're going to buy a car one day, and you're going to be faced with how much you're going to borrow, and what interest rate to pay, and for how long. And it's not always obvious which of these is the best deal. It looks like number 1 is the best deal, but it could be number 2, because it's a shorter length period of time, you're not going to pay as much interest. It's unlikely for these 3 to be the best deal, because the interest rate is so high.
Yeah.
The worst deal by far is number 5. Highest interest rate, relatively long length in years. That's going to cost you a fortune. But just remember, the tricky part is you're going to have to make up an amount. It doesn't matter whether it's 10,000, 5,000, 1,000, but you're going to need an amount that you're borrowing.
Okay.
Okay? Jacob, I will talk to you next time. Enjoy your first day of school tomorrow, and good luck.
All right, well, thank you. Have a good day.
You're welcome. Bye-bye.
Bye.